Hello everyone, I am Manan Tayal and today I am going to present a work on semi-supervised safe visuomotor policy synthesis using barrier certificates. This is a joint work by me, Aditya Singh, Professor Pushpak Jagtap and Professor Shishir Kolathaya. So before we move ahead, let's look at what is exactly safety. So intuitively it means that nothing bad happens, or I can say that if I start in a safe set or safe state, the trajectory of the system should never enter any unsafe state, right? Or mathematically, if I say that a set C is safe when it is positive invariant under dynamics, that means at any time at initial if initially the state is inside the set C, it should always remain in the set C at any time greater than equal to 0. So one of the ways of ensuring positive invariance of a set C is through this concept called control barrier functions. So given a continuous time control system in this way where x is the state and u is the control input, we can always the set C is defined as a super level set of a continuously differentiable function h, such that all the points where h is greater than equal to 0 constitutes the set C, and all the points where h is strictly less than 0 constitutes its complement. So we say that this function h is a control barrier function when there is a extended class k function kappa such that it satisfies this particular inequality. So all the controllers which satisfies this CBF inequality makes the set C positive invariant and thus making it safe. Now, one of the ways of synthesizing a safe controller is through its through a quadratic program for CBF, also known as CBF where we try to minimize the distance between between our controller and the reference controller, such that it satisfies the CBF inequality. Now, if we have only a single inequality, we can very conveniently derive a closed form solution for this, where my safe policy or safe control u is the sum of the reference controller plus a u safe term. Now this u safe term is 0 when the psi is greater than equal to 0, that is it is already safe. Then we don't really need to change the reference controller. But when it is moving towards an unsafe direction, we need to add a non-zero term to the reference controller so that it makes it safe. However, learning such a control barrier function which satisfies all these properties is difficult. So we use deep learning techniques to estimate these to estimate these control barrier functions using neural networks. Now, if we look at neural CBFs, we'll denote a neural CBF by a variable h and a parameter theta for the neural network. Now it needs to satisfy all these three conditions which we have earlier talked about, where h should be greater than equal to 0 at all the points inside the safe set, strictly less than 0 inside the unsafe set, and it should satisfy the CBF inequality at all the points inside the state space. So to learn a CBF that satisfies these three conditions, we need to write a loss function that needs to be minimized to satisfy these three conditions. So to do that, we have a loss function which looks something like this, where we have a max term with 0. So max is taken between the negative of these functions with a 0, which ensures that if there is any violation in these conditions, it'll come up as a positive loss in the loss term, and if these conditions are satisfied, then this term will become negative and I'll give a 0 loss. However, now if you might have seen, we are actually we can only learn these or calculate these losses on finitely many samples, which are sampled from the safe, unsafe, and the domain regions. Now, to kind of counter these errors or learning errors, we actually introduce parameter psi, which basically makes the learning more robust. So the following theorem basically gives us the bound on this psi. So it says that given grid density epsilon and we have n number of points, we can learn a control barrier or h the learned value function or learned function h is a valid CBF if this following condition holds true. Now this gives us an optimal value of psi star that we can derive, and L max is basically the max of the Lipschitz constants of these three loss terms. So in the interest of time, I'll skip the proof, but those interested can refer to a paper for a more detailed proof. So now moving on, we have to now count for visuomotor inputs to synthesize a safe visuomotor controller. To do that, we'll first introduce this concept called world models. So world models are generative AI models that learns the dynamics of the real world. They take into account the special physics and the special properties from the data, and they take in inputs like text, image, video, along with the action to predict the next state. Right. So if I show this pictorially, if at any time instead I my visuomotor input OI is present, I can actually encode it into a latent space, into a latent variable zi, and basically I learn dynamics in the latent space, which takes in the action and the latent variable zi and predicts the next latent variable zi plus 1. Now we can do this, we can continue predicting the next states till a time t, and finally, to make sure that the dynamics that we are learning and the encoder that we are using are correct, we actually match that with the latent embedding of the goal visuomotor state. So we again encode the visuomotor state into a latent space, latent state zg, and we kind of ensure that this is consistent. Now the benefits of using such a world model is that it can help us in generating the required next states, and also it can help us in synthesizing policies or controllers in general. So we use this world model and combine it with control barrier functions to basically learn a safer policy. So what do we do is we basically add a barrier network to the world model, and we try to learn an encoder, a latent dynamics, and a barrier function in a way that the latent space is segregated and is easily separable into safe and unsafe regions. Now as you can see in this small figure, the green dots shows the safe latent embeddings, and the red region shows the unsafe latent embeddings. And to make sure that this sort of setting is realized in the in the in a framework, we actually call this as safety based latent dynamics, or SILAD model in short. And to realize this SILAD model, we use the loss function, which looks something like this. Now if you remember, the first two terms in the loss function are the CBF safe and unsafe losses, and the third component of the loss is basically a dynamics consistency loss. Now if you see the latent next state predicted by the latent dynamics, and the visuomotor observations at time I plus 1 are encoded, and we basically try to make sure that these two are consistent. So this basically loss, when this is low, it makes sure that these two latent embeddings are consistent, and we are able to predict an accurate latent embedding for the next state. Right. So now if we move on to the controller synthesis part, we again use we use a discretized version of our CBF inequality loss, and along with that we use another loss function which tries to make sure that our policy is as close as possible to the user defined or reference policy. Right. Now if you notice, we also have an additional term of eta here. So this eta is actually a robustness parameter to basically counter the modeling inaccuracies in the dynamics consistency loss, and and the following theorem provides us with the theoretical lower bound of this eta. Now it says that if the delta is the maximum of the dynamics inconsistency amongst the samples, then on the training samples, this eta is lower bounded by LB times this delta. Now LB is the Lipschitz constant of the barrier network. So again, the proof is it's not added in these slides in the interest of time, but the interested audience can actually refer to the paper. So now we have actually performed few case studies so to validate our approach. So first of all, we have done it on an inverted pendulum case where it is expected to reach a safe region near the vertical line. Second is a quadruped navigating in a obstacle ridden environment. So you see there is a big red cylinder which is placed in the center, and the quadruped is expected to avoid it and basically make sure that it never hits the cylinder. Now to do that, we have a top we take the visuomotor inputs and from the top side of the top view, and finally we have a track mania example where a race car is expected to run as fast as possible on a racing track, but making sure that it never hits the sides of the racing track. So if we compare our approach with some baselines, some CFRL and imitation learning baselines, we can observe that our method outperforms both these methods in terms of safety rate. And actually in these two cases of inverted pendulum and a quadruped navigation, we observe that the safety is almost close to 100%. Along with that, we also have compared our method with the barrier certificate without the safety guarantees, and we observe that safety guarantees do help us in improving the safety rate of across all the three examples. And despite in the track mini example we were not able to achieve 100% safety rate, but we are still able to outperform all the other methods in terms of safety rate. So thanks a lot for sitting through the presentation, and the interested audience can see through can read through the archive and web page and our web page using these QR codes. Thanks a lot.